Today is our second day of Gears, and we are going to be kind of focusing on more analytical tools. While last week was more like intro and nomenclature, we're going to give you a few analysis tools and then talk about limitations of those. And then hopefully lectures today is not super, we don't want to be super lecture heavy today. We're going to have a few examples, and then the end of it is going to be kind of choose your own adventure for how you guys want to explore high cycle fatigue. But for agenda, we're going over force analysis, like free body diagrams of gears and like nomenclature for that. We're going to go over the Lewis bending equation, which is usually your first pass, like analyzing like how will a gear fail. Conservative theory, we'll talk about it. And then we'll talk about gear fatigue. This video is super cool. There it is. Less boring lectures, great channel, highly recommend. Everything we talk about explained really clearly. Really great video. But come on, Jeff.
Resistant bending.
Wake up, Jeff.
Of the teeth of a gear.
There we go. Okay. To get started, I'm going to give you guys a quick example of how Shigley's handles force notation when talking about gears. Because it's a little difficult because you have to specify which gear is acting on which other gear or shaft and what direction the component is. The subscript tells you what force is acting upon what. So the first one is going to be transmitting the force. The second one is going to be receiving the force. And these apply for both gears and shaft. The superscript gives the direction of how the force is being applied. And when doing gear analysis, like there's two kind of most important ones: radial, so into the direction of like center of rotation, and tangential. Tangential is the really important one because that's how you are transmitting power. And then X, Y, Z are still common as well for just X, Y, and Z direction depending on your coordinate system. For how Shigley's handles gear notation, gears are labeled numerically in sequential order, and shafts that the gears lie on are labeled alphabetically. So like if you have 3 shafts, you'd have shaft A, B, C. And if you have 4 gears, you could have gears 1, 2, 3, 4. And so for a quick example, like F12 is the sum total force of gear 1 on gear 2. F2B is the sum total force of gear 2 on shaft B. And then like FT43 is going to be the tangential force from gear 4 acting on gear 3. So not terribly difficult to understand, but there's a lot of subscripts and superscripts. So like once you get that in your head, it's actually not that difficult to look at. As a quick side note on the bottom note here, Shigley's does a really weird thing where they consider the frame of the machine or the gear train or whatever you're working with to be the first entity. So like if you have a gearbox, the entire frame of the gearbox is labeled 1. And so that means that their first gear or their input gear in Shigley's is often labeled gear 2. I think that's weird, and I prefer my first gear be first. So I just stick to this notation, but if you see anything weird, that's why. That's not super important, and there won't be like questions on your homework around that, but just something to keep in mind. So for a really simple set of like just 2 gears enmeshed with each other and transmitting power. As a reminder, sometimes the smaller gear is referred to the pinion and the larger gear is called a gear. Why they have to distinguish between that, I don't know, but that's why. We have 2 gears in mesh, gear and pinion. The pinion is going to be called gear 2. That's your input. Your larger gear is gear 3. That's receiving the torque. And the the force, as a reminder from last week, is transmitted along a pressure line or the line of action at an angle phi. Historically, that has been 14.5 degrees. But these days, it's more common to see either 20 or 25 degrees. So like a standard gear set manufactured by like a well-known reputable manufacturer is going to have these pressure angles, most likely 20 degrees, but sometimes 25. If you want some like insight for why you have different angles, a larger angle can mean you can do more force, but you also have more radial force going into the gear. You guys should pick up the book, or maybe consider what if happens if you have weird cases that don't have these standard degrees. Or you could look at very weird gear trains like segways. Segways have interesting gear trains. You should look into that. Yeah. They also, like, as a fun fact, they primarily have a prime number of teeth on their gears, meaning that the same gear, when it's in mesh with another gear, is very rarely coming into contact with the same gear teeth. So like if you have, like, for example, if you have if you have like a 22, if you have a 20 teeth gear and mesh with another 20 teeth gear, the same gear teeth are going to be coming into contact each individual time. But if you change it, you'll have rotating ones. And if you have it prime, the same gear teeth will be coming in contact even less because don't have the very common multiples. So this is the gear train we're going to be analyzing. For the first input gear, very simple, like free body diagrams case, you have the force of the reaction force from the other force acting on that line of action. And additionally, you have both the like X and Y component and the torque that the shaft is applying onto the gear. So you should only have 3 forces acting upon your gear. For the larger gear, you should see a similar case, and hopefully unsurprisingly, the force of the actual gear tooth should be equal and opposite as your original one. So for our first gear, our force is acting on top. It's in that bottom left, pointing the bottom left. Our second gear on top, it's pointing the top right, equal and opposite. It is useful to then take those gear trains and break into the composite component forces. You want to break up those forces into the radial and the tangential direction for each of your individual forces. The shafts, you don't care. The shaft forces, you don't care as much, but those forces from the gear are very important because that tangential force is what is transmitting the transmitted load. That's usually called like WT. Sometimes the T is in the subscript, sometimes the T is in the superscript. They're not always consistent with it, but whenever you see tangential load or like power transmitted, this is what they're talking about. This is important because this is what carries the torque. This is what actually is transmitting power. We don't really care about the radial power going in because it's not transmitting power. It's just applying stress to the gear, but you can't have a perfect 90-degree just because like geometry. So WT is what we care about when we're doing free body diagrams for gears. Going from WT to torque is a really simple equation. It's still R cross F, except now because we've already made this into a tangential force, when we cross that with a radius, it's the same as just multiplying it. So very commonly, you'll just see the pitch circle of the gear divided by 2. So you have your radius of your gear multiplied by your tangential force. Really simple question, same as just high school physics. Going from torque to power is also a pretty simple equation, and how a lot of gears and gear trains will be rated of like, what is your output horsepower or power for your gear set. Power, which in Shigley's, they use capital H to designate because P is usually reserved for pitch circle or diametral pitch, depending if you have capital P or lowercase p. That is just your torque multiplied by your angular velocity. So this equation right here is true for all units. And depending on what your input parameters will be, like you might have a weird unit for power. Actually, sorry, I'm getting a little ahead of myself. That's true for all units. Before I talk about velocity, it's useful to remind that gear trains actually have a pretty high efficiency. The frictional losses from energy transmitted between gears is usually like less than 2%. And so that equation for power, you don't really need to consider, or like you can abstract it so that you're only considering both gears as equal power outputs. So you don't need to designate between, well, this is the power input of the first gear, this is the power output of the second gear. Less than 2% losses is relatively small considering like what we're going to be doing useful work for. So for abstraction, we're just going to keep it the same. If you have power as constant between either gear set, and this is again a reminder of last week, it's also useful to keep velocity between the two gear sets as well. So if you remember, you have two rolling cylinders in contact with each other, you have a constant pitch velocity at where those two gears come in contact. This is useful because when we're looking at the power output of both gears, like you need to consider angular velocity. So we want to then calculate what is the like linear pitch velocity for those 2 points. That we can calculate really easily with this equation here. So this is for customary units right here, where your velocity is usually going to be in feet per minute. It's just the gear diameter, your gear speed in angular terms, and go through. If you want to put it in all terms, it's just a simple equation there. This is all a lot of slides and just pretty simple formulas to come down to power. Power output is what a lot of gear trains will like be rated for, and you'll see a lot of gears. What you are taking, if you want to put that power output in horsepower, you take your transmitted load in pounds force, and then use this equation in pitch line velocity for that constant velocity between the two intersecting points. Very similar form factor for if you're doing your power output for a like metric unit. So that's a lot of slides and information. Let's do some little practice for this. In this set, we have a input gear and an idler. Gear 3 is just an idler gear. An idler gear is purely used for, because every time you have two gears come into contact, one's going to be going clockwise, one's going counterclockwise. Idler gears are commonly used to reverse the direction of a gear. They're not used for transmitting torque. They're just used for like reversing the direction of a gear, commonly meaning there's not any torque supplied onto the shaft. We have input gear 2, because Shapley says that weird notation, in the bottom right corner with a 20-tooth gear. It's rotating at 1750 revs per minute and transmitting that amount of power. What this question is going to ask you to do is make and solve all the forces acting on the idler gear. So figure out how much power it's transmitting and what the shaft forces are acting upon that gear. If you're looking for a hint for how you would go about this, it's also worth mentioning these are metric gears because instead of giving you a diametral pitch, they give you a module. So getting you accustomed to both units. Modules, if you go back to the slides from last week, you can remind her, but it's the ratio of the number of teeth to the pitch diameter. So I would go from find the pitch diameter from the module and the number of teeth, calculate the translated load from how much power is going across, and then from the radial forces and the pressure angle, because we have a standard pressure angle 20 degrees, you can calculate the transmitted force and radial force, and then from there you should be able to calculate the shaft forces acting upon the gear. I highly recommend going to the whiteboard because I want to move. Ooh, yay! Actually, I had a break. No. Why is it Sonic? What the heck? Harder time. Cold. It's kind of impressive. I don't know. That's too good.
You really made us think of you. Yeah.
Oh, yeah.
That was really fun. Oh my God. I think you're always been exploding. Yeah. You're confused. This way. Nothing to.
This lecture would have been so useful. Connected.
Oh, really?
I just had to watch all the less boring lectures videos to figure out how to do gear analysis. But they did not explain it.
I guess if we had more time, like, and this was a 4 credit class, I would have loved to do because, and in Mech Pro, Daniela does a really good like, okay, like here's the basic like gear nomenclature, so stuff we did last week, and then she has you to go and like make a gear clock assembly together, and like you learn how to use, you learn like, okay, here's my pitch diameter, here's how far apart I need to put them, and here's how I do like gear mates in SolidWorks. Like it's a really useful tutorial. And I would love to like actually design something, but alas, 2 credits. Bro has shared the MechDev slides with me, and I skimmed through them, and like there's still some useful stuff. I could see how it'd just be,
But that wasn't that class was like just so information dense.
yeah.
It was just so much lecturing that like it just none of it was routine.
Rojo said Dave likes to set a denim into denim a lot.
Denim.
Yeah, like top half of the gear, bottom half of the gear, like from the pitch circle. Wait, that's it. Hold on. I think I have the metric one there. The metric one should be there. Yeah, yeah, this equation, because you were in SI units. So,
I literally keep the other three.
It's, there, because, like, because there's two different stickers, like, you have doing your teeth analysis problem. Metric customary.
And also, why is this good? I it's just the- I-
it's been a good chalk and talk example, actually. Like working together. Okay. Do that next time. Be next year. I've had too many first years and sophomores come up to me like, "Oh, when's the next time you're teaching this class?" I was like,
Get a PhD real quick.
"Yeah." Uh, how's everyone doing? Like maybe 2 more minutes? Yeah. Okay. Well, we can walk through it after 2 more minutes, or if you need more time. No pressure. Good smoothie. Good soup.
the meme where it's like if you put banana in any smoothie, it just like overpowers all the other fruits. Is that the case here?
I'm getting mostly strawberry from this, but I think it is strawberry banana.
I thought it was,
Oh, no, I think you're right.
oh, there is no banana in it.
Mm.
I don't know why I thought it was. I think every smoothie has banana.
Banana, like, easily different those.
Bring back the smoothie bar. You're gonna break like 30 blenders, but it was worth it.
Yeah, that would sound nice.
Right.
So last.
Mhm.
No, and then she did like $3 open it, and then there's like 2 or 3 of them in the freezer, like ice cream.
Oh,
If you blend up enough banana with little enough milk, then it's like. scoopable. Wow, I'm so healthy, it's like banana and fruit and Nutella, don't worry about it.
if you're still working on it, no worries. Just so we have the time to go the rest of the lecture. So from these suggestions, like, and you guys can read the actual solutions, they're really tiny, but basically like from the module, you multiply that by the number of teeth to get the pitch diameter. From there, once you have the pitch diameter, you already have the force. You already have the power transmitted, so we can substitute this equation around to get how much force is tangential at each applied tooth. Once we have how much force is tangential, we know we're working at a 20-degree pressure angle for each of these forces here. So we just take that relationship to find, and tangent to find the radial force. And then since we're treating this big gear as an idler, we're just saying the power in, power out, the force and the tangential and radial forces are going to be equal over here. And then once we have those options, all we have to do is combine, like these gears are mounted at 90 degrees from each other, so they're already aligned with our XY axis. So we don't have to do any funky stuff there. And then we just take the radial and tangential components and add them together by Pythagorean theorem, and we get the radial forces acting on, or we get the shaft forces. So you guys can go through these slides, just double check. Is there anything there that like didn't make sense or confusing on like why the idler works that way? Peachy? Banana-y? Let's ride. Okay. Let's start talking about gear failure. Gear failure, there's many analysis angles that you can take. Shigley's mostly goes over AGMA, the American Gear Manufacturers Association. I looked it up. They have a conference in Disneyland this year, so I think we should go. It's in March. I'm just saying we pool funds. Ooh, yeah. We should go. So for the actual like analysis they take, they just have like decades worth of analytical and experimental data that they've made into like literally hundreds and hundreds of charts. We're not going to go through all of those. We're only going to pick up like the design highlights, but basically they have 2 methods. They design for strength and static failure, and they design for wear for high cycle fatigue. To get started, we'll talk about designing for strength and using Lewis bending equations. Woo! So for low cycle failure, where you're not designing for like lifetime, or you're just mostly concerned like, am I going to exceed the yield strength of this? You can, like, for a first order approximation, you can say that a gear tooth is essentially just a cantilever beam. So all those tools we've spent a lot of weeks on at the beginning, whoa, they're useful. No way. So for modeling the gear tooth as a cantilever beam, you remember all of those tables I showed you guys earlier when we were going over like superposition and other stuff of analytical tools? There is a rectangular cantilever beam with face width F and thickness T. And you can substitute that in to your beam bending stress equation, M over I over C. Sometimes MY over I, you'll see MI over C, where I over C is equal to your section modulus, because that is only dependent on the geometry of whatever your beam is. So it's the same exact formula, just rewritten sometimes other way around. You can substitute these in and get an equation of like 6 times transmitted load times the length of your tooth, the face width, and the thickness. That's not super useful because there's still a ton of design parameters specific to your gear tooth. But if we go to the next slide, and not math that I won't walk you through, but it does exist if you want to go look at it at Shigley's. If you use, like, this is the same gear tooth as before, if you use the thickness of the tooth and distance away from the root, as well as the F is coming out of the page here, your face width. You can use similar triangles and similar geometries to allow you to simplify this even further. And also because spur gears have a set involute profile that's pretty standard for all spur gears, you can simplify this even further to an equation like this. This is the most like pure form of the Lewis bending equation, where you have your transmitted load, your pitch diameter, if you're working in customary, the face width, so how thick your gear is, and then Y is called the Lewis form factor. The Lewis form factor you can calculate from here just based on the geometry of your tooth, but because we are using basically standard like stock gear geometry that like the equation's been solved already, it's more common to take this equation and for Y, just look up on a table. So like, again, transmitted load, diametral pitch, which will be in inches, face width, and your Y factor, which is unitless. Your Y, like Lewis bending equation, it's really important right now, and I want to highlight this. Maybe I can actually circle in the slides. This table is only valid for spur gears with a pressure angle of 20. There's if you're looking at like bevel gears, if you're looking at helical gears, if you're looking at other gears with different pressure angles, this table is no longer valid, and you'll have to go to like the AGMA or the appendix in Shigley's and pull a different table. But it's really important that like in the grand scheme of engineering, when you are just pulling tables, like you pick the right fudge factor that actually works. There's a second aspect to this as well. So this is for like the static case where you're just analyzing gear teeth. There is other factors you need to consider this as well. Your dynamic factor is usually called KV, and it's affected by how fast you're rotating. So that pitch line velocity were 2 rolling cylinders in constant contact with each other. What they did is that they took that first cantilever beam assumption, played it out a little bit, futzed with the geometry, and then they did tons, like hours and hours and days of like experimental testing where they just had 2 gear trains going, and then they had churning at different speeds. And they were getting like the first order approximation got you in the right ballpark, but there was still a little bit more fudge factor that you needed to add to it. That's where the dynamic factor comes in based on how fast is your gears spinning. Because like the faster you go, the more load you're going to have obviously from dynamic effects. As well as how your gear teeth are manufactured. So when you're working on customary, your KV factor is going to be dependent on how fast you're spinning. So once again, your velocity, your pitch velocity that we calculated earlier, I showed the equations for. And then these are very common manufacturing methods, you pick which one is set. So like when you look up, if you go to practice problems in Shigley's, they will explicitly say you have a cut or a milled profile or a hobbed or shaped profile. If you go to KHK or any other gear manufacturer, they're going to have like, this is how these gears are made. They're casted or whatever. This is for customary. This is for SI or metric units. Once you have your KV factor for how fast you know you'll be spinning, plugging that back into the Lewis bending equation is pretty simple. And this formula right here, this equation is like your set equation for this is how I'm going to run everything. So if you're in customary, you're going to be using these units. You're going to be using this formula. Always check your units. So I put them explicitly here. Your Lewis bending factor should be unitless. as well as your dynamic factor. So you just want to make sure that your bending equations make sense if you're putting pounds force or you're using inches down at the bottom. If you're using the bending equation already transmitted into pascals because it's more common when you're using metric to use millimeters rather than just straight meters. So you want to keep that in mind where you don't want to have you don't want to accidentally put kilonewtons there or something like that. So those are the two equations for like the Lewis bending equations and static failure or low cycle. There are some like not downsides to it, but there are some like limitations to it. This is a pretty conservative formula. It's usually your first base. Like I wouldn't go do these equations and then just be like, okay, my gear train's ready to be assembled. It assumes one tooth is taking the full load of the entire like gear train, and that the full load is applied like to the middle of the tooth, like right where that pitch circle meets the diameter. It's good. It's very good and useful for a first pass understanding of what your stress state is going to look like and what the nature of bending is. However, you should verify this with either like testing if you can, or some FEA models with more than one element per tooth. Okay. More chalk time. Yeah. We have another problem here. I'm going to leave this up here. There is again, as with before, there is like a recommended steps suggestion page you want to go. I think it'd be cool. Oh, I don't have another laptop actually. Can I borrow someone's laptop? I'm going to chalk and talk it over there if anyone would like to join. But thank you, sir. Let's spend about maybe 10 minutes on this. I would be awesome. Oh wait, no. Oh wait, yeah. Well, that this chat over here needs to be this. Wow. Thank you, sir.
Oh my God. That's fine.
And saving that.
No.
Oh.
So little, a big key.
Yeah. Sorry. So this really is really confusing. I would recommend pulling up the last
Yeah.
slides as well. Diametral pitch. So yeah, it's wonderful. So the diametral pitch is how many teeth you have per inch, like along here, right? To get the pitch diameter, which is the diameter of the circular pitch, you just take how many teeth you have divided by your diameter. So you should get a diameter.
And then the law.
Wait, is it diametrical?
I D N. Well, what is that?
Okay, diametrical pitch.
There's too many terms that are too similar sounding and are basically the same thing.
Okay,
That was you, that's why I'm on.
Oh, you're right. Yeah, yeah.
1.5 inches eight.
Sorry.
Yeah.
Oh, that makes sense. Yeah. Oh, we're gonna convert that to green.
And 16.
So,
Faculty is diameter of 1. Or grade is.
What is the?
Circular.
diameter, radius.
The-
Pitch diameter is the diameter of your circular pitch. The circular pitch is like you have small ears.
Bodily cylinder
Thing.
meters. No, which one? We're wearing. Yeah.
Yes,
Inches.
diameter right there. Is your
It is.
pitch diameter.
Times radius per second.
And the entire circle.
No, it's right.
Oh, it's like a circumference.
It's like the circumference of like where you like mid to.
Okay, so you have this and this. What do you want? The stock for the, oh, okay.
Good. So the long specify
Next.
dynamic factor. What the definition is, and it's in inches per second. But the answers is, it's, I mean, I guess.
I know what it's like.
Okay, what are you writing? 65.
I don't know if you.
Okay, and then you go to our speed thing. Where is that? Where is it?
I just saw.
Wait. And this one. So, sorry. Inches, there's 39.37. 1 point.
That was.
Okay. Second, we're going to represent to radians per second. Radians is you.
Wait, where is
Inches and radians. That's very fast.
Or, no. That's like, I don't know what it is. Oh.
Oh. This is. I'd like to. Then we're.
The next.
We need more letters.
We have more letters, no?
Yeah.
We also have like a Greek letter.
Yeah. Even that is, like, for reference. But.
It's Scott. What do you think that means?
Just the standards for a gear. They shouldn't really be considered for your calculations.
I mean, what's the use for a dynamic factor? Like, if it passes nil.
Uh,
Thingy.
Well, that's very common.
Okay, so then we still run it. This is for reference, y'all, they use some kind of middle years. Find that for your dynamic.
This one.
We're gonna do.
Yeah. Make sure you're in the right units. Are you in customary? Yes. Okay. I got all. Using the right font, random 1, 2, 3. See what the other 100 is. That was easy. Right there. I wired. Zoom folks, how y'all doing? Any questions?
We're doing okay so far.
Yeah.
Actually, that's my A factor of 1.3.
That's close to what I got.
I took the middle and the top.
That's, you know what? If that's the assumption you want to make, sure. That's good. Well, we're awkward. I'm curious. So keep going down this path. We'll see how far away.
Very different than the graph. The graph would indicate like 1, like, you know, 5 blocks.
Oh, is that?
Yeah.
Oh, the graph that's on there.
Pretty confident.
Okay, I'm gonna be so honest. I was trying to find a good
Yes.
Or
KPSI.
What was
Slow
your?
just for a second. I
Oh, yeah.
recognize it. Where everything's the SI
Oh, I see.
Freedom units.
So rather than that, what does this give you?
Well, I was programming this like where. Oh, yes. 1.1.
That's like,
That's a part.
I think as you already have it, like put it like a.
Oh, because that's for like multiple.
I would be honest with you.
It is more of a like trend.
Yeah.
I'm gonna use this problem.
Yeah, I guess you should have after.
Oh, they should,
What is formula used there? Fast lines. Yeah.
oh.
Do you guys have like a, you guys have a wire EDM manufacturer?
No.
No, okay, because we need, I know Baja needed to do some next semester, but that, well, for the mating surface, for hubs.
We have a belt that. You mean like for, we have like tri-load, like you mean like tri-load to my spline?
Yeah.
For that interface? Okay, I have no idea.
Belt that rotates the whole shaft. And then we don't have
Interesting.
splines.
Okay.
It's spring.
Interesting.
In some ways, I'm bullish.
I know. Interesting.
Output from the motor.
Go-
rotates
goes.
the whole shaft.
Let's go.
Three laser cut hardboard gears in the middle. Were they called key belts? Key belts?
Those exist.
Yeah, I know.
They're
They're real.
there's Northeastern used one
Oh,
for
no.
their for four-wheel drive for Baja.
Just like one big one.
No, not for the entire thing. No. They didn't do chain drive. No, they had a prop shaft. But they had a really weird gearbox for connecting that had one of those like metal, like it was like a metal timing belt. Like
No.
what's popping?
What is Sigma?
Sigma is bending stress. So remember these, like, so in general, sigma is going to be stress state. There's varying kinds. This for bending, like the Lewis form factor or the Lewis bending equations is an adaptation of the bending stress we spent a lot of weeks talking about, like my over I. They convert that into like our first level assumption was we're saying our gear tooth, which like looks something vaguely like that. Like this, essentially, I mean, it's my fixed surface. This is all of a sudden a cantilever beam. And I'm saying the majority of my stress is coming from the bending stress of the force along that.
But that's what we have.
Oh, I'm making this so bad.
Okay, so how many is this?
So cool.
But you still need that. And, how do you?
So you have here, you have the diameter.
Oh.
So you're gonna go back to that equation. Oh.
Okay.
We're gonna go back to that equation of. Go back to.
What happened? I don't know that.
Oh, no. Sorry. So what we're looking for is you want an allowable stress. Basically, so we have, so the yield stress here is 30 kPSI. Remember, I want to use the same factor of 3. So 10 kPSI is our allowable bending stress. So then we have that now back to this equation over here for this equation over here. Our allowable bending stress is 10 kPSI. This is the PSI. So change that up. And then we can calculate, we have our dynamic factor, we have the actual pitch, yeah, basically. We have our, sorry. Sorry, I got a little. No, I'll start the logic there.
Yes. Okay. Wait. What was the width of it again?
it's really. No.
Right, okay. Now,
0.29.
10 ppm, is that cute?
You shouldn't have KPSI. That should be, it should be, it should be.
Divided by what?
Yeah, but I.
So we can calculate it. So we have the formula right here.
On the.
For any direct.
I just wait for the letter.
Yeah.
Yeah, that's perfect. Yeah, that's perfect. Maybe instead of just, we want to set that equivalent to more interest stress.
Oh.
And then incorporate our design factor. So that now
Why didn't you put it
define- It'll make it-
But it could be totally wrong. See.
Okay, cool.
That makes sense.
Yeah. Cool. Okay.
No, I'm good. I finished. Everything I did. So far I think only two. We had like, I had like 7 people sign up and people graduated. Some got cold, someone decided they were only gonna do the miles and the beverages.
Oh, did you do it, Carlos?
I knew the answer.
The whole thing? Oh my gosh.
How long did it take? I started at noon on Saturday and I finished it around like 8:30 on Sunday. I woke up, yeah, I was planning, cause like, I scheduled it around the miles, so I ran 8 miles. Took like a 30-minute rest. So I probably should have rested a little longer than that, but I didn't. Then I ran 2 miles and I was dead. So I like stopped at CVS and just like chugged like 2 Gatorades there. It was so dehydrated, so hot. That ran another 4 miles, so 14 miles. And then I was planning like, okay, in the morning of that, I'm trying to 2 more miles. But then like, it was around like 9 hours. Happened, I was like, I'm not gonna be guys super. Or the late when they got the morning, I'm just gonna bang out 4 miles right now, so I just did in the East. Finished that and then just like plugged away at the donuts throughout the day.
Wait, the Centurions, how did you join it?
So in the most traditional sense, this started as a cross country like meme and like challenge things because those kids are freaks. In the most pure form, it's supposed to be pure, but like you can read one, like I announced it, like I'm not gonna be tracking you or keeping you honest, like so like I mostly did beer. I did have one tequila shot and
There were, how did we do this?
yeah.
Did you have me assigned though?
No.
Oh.
I
Sorry. I really wanted to do it.
Yeah, track.
Go for a soccer. We just make them, we both went with this.
Yeah.
Okay. That honestly, that was.
I literally, I had posted on 6 donuts just because I wanted donuts, and I Googled them. And the drawings happened to me. Carlos, both think that you're an idiot and I'm kind of proud of you.
There we go. I
365.
That's how I feel about that stuff too. Like, I don't regret doing it. I will never do it again. Like every single time it's happened at Olin, I haven't been able to do it. I need to.
Congratulations.
Is that it? Yay.
50,000 is pounds.
I'm so excited for 2020.
Rated.
I'm so excited.
what equation are you using for that?
What value did you get for your
You
transfer?
get a gallon of water. Pour out of the water.
That should, so that should just be a force. So you're in the right range, but I think you have the wrong units. Transmitted load should just be.
So it tastes like Gatorade,
So that-
it's crazy.
I just put that.
And so,
Wild.
it's so fun.
Radiance and.
We did it, and then they
Oh, you
like
think it was
came up
power.
later.
Oh,
and
so
they were,
that-
like,
that's-
freaking bored, and I was like.
No, 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 no,
I was like, "Oh."
No, I didn't
And
know.
I did it. Like, you guys get-
Oh my God.
Yeah.
What was your name? Like, I did 1,000 smoking for the day.
And you're you stay hydrated, it's fine. Exactly that.
I get, yeah, I get like.
I think it could be like maybe.
Okay. For 50,000.
Actually,
but I'm just like misery, you know what I mean? Like.
Yeah, because I think, well, that should be
And
in,
it just comes from-
Yeah. More viable side.
if you use it, so if you convert that. So that is the unit of power. That is the unit of power. I don't think it's.
So if it's like
standard one.
constantly. Finds.
What is the customer unit of power besides horsepower?
That's not okay for every interaction that I have.
Yeah, for units.
I see my friend.
Because there's a niche one that I think is 8 pounds per second.
Slug, and then I was just saying foot pound per second.
Is horsepower, that's like.
You should be getting around 7 horsepower.
Yeah, 7.5.
Nice.
Okay.
Yeah, so so the equation, Shigley answers gets it closer to 7. You have a slightly higher answer because your dynamic factor was not as high. But like they didn't explicitly say that. So like they said,
What's not it? Got me to-
Yeah.
No, I have.
No, I haven't.
So I, did the-
In this case, you want to solve. And then, you do want to finish this over, so what you can do then, just as these equation, this is more or less. Yeah, right, you then put your answer.
Oh, my God, it doesn't have to.
I mean, other than.
a slug is this current unit of mass.
Right.
In the standards. What? I've never slinched it. I mean, I've been. The one. You could do 12 slug. I hate that.
Oh, where's the thermal unit? Per hour, yeah. British thermal unit per hour. It's British people. Electron full hour.
I like, Matt, like, I like, you know how
Like it's.
the further derivatives of like, snap, crackle, pop, and then, you know, which is really just Rice Krispies.
And then I also know.
When did that
Yeah.
declaration in some
It's weird.
George, yeah, George.
And I did, after it gets in snap.
How y'all two doing?
Cool. You guys get like 7.
Nine.
Perfect. Beautiful.
Or there is snap slash jump, so yeah.
I can do that.
Stay here.
Which-
Okay. Not to interrupt, I do have a few more slides that I wanted to introduce y'all to, and then the rest of it is kind of open time to explore what you want to. If you want to finish the practice problem or homework or read the actual thing I'm asking you to read, that'd be sick. Solution set is in the slides. If you're looking at that, you should get something around 7 range. Might be a little different depending on KV factor is, but again, and they have a note about this at the bottom. These are for estimates for preliminary analysis. You should use testing or FEA or other tools to verify your results. Mileage may vary. Okay. I want to talk about high cycle failure real fast and give a quick review of what Nathan talked about a few weeks ago. So at higher cycle counts and for a lifetime analysis, your failure is going to come less from your like bending at the tooth and more from surface wear. So there'll be a lot of pressure from gear teeth, obviously. So just to give a few slides overview of what Nathan talked about last week, you guys should review Nathan's slides. Like rolling contact or other surfaces between can, like for over like cycles and cycles and cycles, order of magnitudes, like adds more and more load to the bottom of it, where you eventually start getting pitting and spalling, where pitting is just like when you have different surface contact ratios pushing into each other, you'll have weak spots that eventually start forming a pit. And then very soon after the pit starts forming, like the surface finish is going to very rapidly decay and you're going to have less and less material there. And it's going to very dramatically reduce your teeth. On a bearing, this is what pitting looks like after just like cycles and cycles of like pitting. For what gear teeth look like, you have something more to this effect, where after like several years of running on mills, lace, whatever you might have with gear teeth, you will have like pitting that starts happening like on your gear teeth. Notice they look awfully concentrated right near the center line. Wonder why that is. Could that be where it's coming into contact? Oh, you also notice that this is a helical gear set right here, so it has more and more and more engagement the further up you get. So that's why it's also kind of like gradually increasing. It's not evenly over the entire tooth. For high cycle failure, it's very similar to shaft loading, whereas you're going to have a bunch of like factors, some like similar to the endurance limit modifying factors, Marin factors. You're going to have many. You're going to have a lot of those that come together depending on the geometry, surface finish, size, et cetera, et cetera, et cetera. So you can apply those to your bending stresses, and you can also apply that to like how resistive it is to your to pitting. And so what you do is that very similar to shaft loading or like endurance modifying is that you take the corrected bending strength for how long, like when something will fail, and the corrected contact strength for how resistant it is. Remember, like it is inversely related to the hardness of a material. The harder your material is, the more resistant it will be to pitting and spalling and other surface wear. You divide that by whatever your contact stress is or your bending stress. There are far too many factors for me, and I think to just walk over, and I think it'd be a disservice just for me to stand here for another 25 minutes, just pointing at graphs and vaguely talking about them. So I'm going to give this a choose your own adventure path, where you either can read the chapter in Shigley's or the slides that a lot of we're adapting this material from that transfer class I took. Those are posted onto Canvas. So you have like kind of choose your own adventure of either going to the Canvas page and reading the slides, the lecture slides on gears from like page 55 forward, or picking up Shigley's. There's a physical copy right there. There's also a copy on the Canvas files, and going from section 14.2. you guys can either spend like around 15 minutes reviewing over the content, just seeing if it makes sense. Like I don't expect you guys to have any of this memorized. I don't. There won't be a homework question on like pitting resistance, but like talking about that is what we just want to introduce y'all to for seeing like what factors affect the lifetime of your gear. Post like for like, to be honest, like anything that we design during your time at Olin, you're probably not going to do high cycle analysis on it. So like the Baja gearbox, like is not being run enough for us to care about pitting. We care more about the root stress. But it's something that exists. And if you're doing like machine element design, you should know about it. If you finish that, there is another cumulative, like bring it all together. That gear problem we just did, where we're solving for how much horsepower is it outputted for. I want you guys to, if you want to, you could estimate what the final horsepower rating would be based on an infinite life and bending and bringing in your prior fatigue life. This is example 14.2 in Shigley's. It's a really cool one that like sums up a lot of the stuff we've done so far. And you guys should take a look at it. But other than that, you can either finish that problem, you can work on some homework, go over those slides, go get coffee. Yeah, that's it for lecture today. Kind of like closing remarks. Next classes are going to be belts and bearings. So you guys should submit homework corrections. Daniel, thank you for pointing out an error we had on homework question 3. We will make an announcement about that. But